Episode 26, The Arrow of Time. Why does time move forward? In the last episode, we asked whether the past is still there. We looked at the strange possibility that past, present, and future may all belong to a larger structure of space-time, rather than the present being the only thing that truly exists. But even if that idea is right, it leaves us with another problem. If past and future are both part of reality, why do we experience time moving in one direction? Why do we remember yesterday but not tomorrow? Why does a child grow into an adult, but an adult never naturally becomes a child again? Why does a glass fall from a table and shatter, but the shattered pieces never leap back together and form the glass again? This is known as the arrow of time, and it may be one of the most important clues we have to understanding what time really is. At first, the answer seems obvious. Time moves forward because that is simply what time does. We wake up, live through the day, and go to sleep. Morning becomes afternoon, afternoon becomes evening, and today becomes yesterday. Everything about ordinary life tells us that time has a direction. But when physicists look at many of the basic laws of nature, they find something deeply surprising. On the smallest scales, many of those laws work almost as well backwards as forwards. If two billiard balls collide and you watch the film in reverse, the backwards version still looks physically possible. If the Earth orbits the Sun and you reverse the direction of the film, Newton's laws still make sense. Even much of Einstein's relativity does not automatically tell us which direction is the future and which direction is the past. The equations often describe relationships between events, but they do not always explain why one direction feels like time moving forwards. So, where does the arrow come from? The most important answer we have is entropy. Entropy is often described as disorder, and that is a useful starting point, although it is not quite the whole story. More precisely, entropy is connected with the number of possible microscopic arrangements that can produce the same large-scale appearance. A neat pack of cards has low entropy because there are very few ways to arrange the cards in perfect order. A shuffled pack has much higher entropy because there are vastly more ways for the cards to be mixed up. If you shuffle a deck, you expect order to become disorder. You do not expect a random shuffle to place every card perfectly back into suit and number order, not because it is impossible, but because it is fantastically unlikely. The same idea applies everywhere. Put a drop of ink into a glass of water, and the ink spreads out. The molecules move randomly until the color becomes mixed throughout the glass. There are enormously more ways for the ink to be spread through the water than there are for it to remain as a neat drop. Leave a hot cup of tea on a table and it cools. Heat spreads from the hotter tea into the cooler room because there are far more ways for the energy to be shared around than for it to remain concentrated in the cup. Crack an egg into a bowl and it mixes. Burn a piece of wood and it becomes smoke, ash, and heat. These things do not normally reverse because the reversed state would require an almost impossibly exact arrangement of countless particles. This is the second law of thermodynamics. In an isolated system, entropy tends to increase. That word tends matters. The second law is not quite like a commandment forbidding the reverse. It is a statistical law. It says that for large systems made of enormous numbers of particles, high entropy arrangements are so overwhelmingly more common than low entropy arrangements that the system almost always moves towards higher entropy. A smashed glass could, in principle, reassemble itself if every fragment, molecule, and vibration reversed in exactly the right way. But the probability is so tiny that for all practical purposes it will never happen. The pieces stay scattered because there are unimaginably more scattered arrangements than there are perfectly assembled ones. This gives us one of the clearest ways to understand the arrow of time. The future is the direction in which entropy increases. We know the film of the breaking glass is running forwards because the ordered glass becomes disordered fragments. We know the film of smoke leaving a chimney is running forwards because the smoke spreads into the air. We know cream mixing into coffee is running forwards because the neat separation of cream and coffee becomes a blended mixture. These events show us the direction of time because they show us entropy increasing. But that raises a deeper question. If entropy explains why things move from order to disorder, Why was the universe ordered enough in the first place for entropy to increase? If the universe had always been in a state of maximum disorder, there would be no strong arrow of time. Nothing much would happen. There would be no useful energy gradients, no stars burning, no planets forming, no life, no memory, no clocks in any meaningful sense. The reason we have an arrow of time today seems to be that the early universe began in a very special low entropy state. This part is subtle because the early universe was hot, dense, and full of radiation, which sounds chaotic. But from the point of view of gravity, it was surprisingly smooth and uniform. Matter and radiation were spread out very evenly. That smoothness was special. Gravity tends to increase entropy by allowing matter to clump together into stars, galaxies, and black holes. So, although the early universe may look messy to our ordinary imagination, gravitationally it was highly ordered compared with what it could have been. Over billions of years, tiny irregularities grew into galaxies, stars formed, stars died, black holes appeared, and entropy increased enormously. This is why the arrow of time is not just a local story about broken cups and cooling tea. It is a cosmological story. The direction of time we experience in our kitchens, our bodies, and our memories may be connected to the condition of the entire universe shortly after the Big Bang. We live in the aftermath of a low entropy beginning. Every burning star, every living cell, every thought in your brain, and every clock on your wall is part of a larger movement from lower entropy towards higher entropy. This also helps explain why we remember the past but not the future. Memory is a physical process. To form a memory, your brain must change. Energy is used, heat is produced, and entropy increases. Records of the past exist because the past has left traces in the present. Footprints in mud, fossils in rock, photographs in albums, scars on skin, and memories in brains are all physical records formed through irreversible processes. The future has not left such records because, from our point of view, the physical processes that would create them have not yet occurred. We are not simply choosing to remember backwards. The structure of the universe allows records to point in the direction of lower entropy. Cause and effect may also be tied to this same arrow. We say the thrown stone causes the window to break, not that the broken window causes the stone to have been thrown. We say the match causes the fire, not that the fire causes the match to have been struck. Our idea of causality follows the same direction as increasing entropy. Causes leave traces. Effects spread information into the world. Once the stone has broken the window, the information about that event is carried into cracks, sound waves, displaced air, human memory, and perhaps a repair bill. Reversing all of that would require the universe to arrange itself with absurd precision. There are other arrows of time, too. There is the psychological arrow, which is our experience of remembering the past and anticipating the future. There is the thermodynamic arrow linked to entropy. There's the cosmological arrow connected with the expansion of the universe. There's the radiative arrow because light spreads outward from stars and lamps rather than naturally gathering in from all directions. These arrows appear to point the same way, and many physicists suspect they are connected, with entropy playing the central role. But exactly how all these arrows fit together remains a deep question. There are also tiny complications at the level of particle physics. Some processes involving the weak nuclear force do not behave exactly the same when time is reversed. These effects are real, but they are extremely small compared with the everyday arrow of time we experience. They do not explain why eggs break, why people age, or why smoke spreads through a room. For the large-scale world of daily life, entropy remains the main explanation. So, does entropy solve the mystery of time completely? No. It explains why many processes are irreversible. It explains why we can tell the difference between a film running forwards and a film running backwards. It explains why we remember the past through records and traces. But it does not fully explain why the universe began in such a special low entropy condition. It does not fully explain why consciousness experiences a flowing present. And it does not tell us whether time itself is fundamental or whether it emerges from deeper physical laws. What it does show is that the arrow of time is not merely a feeling. It is written into the physical behavior of the universe around us. Every cooling cup of tea, every burning star, every aging body, and every fading footprint is part of the same great pattern. The future is not simply later, it is the direction in which entropy increases. The past is not simply earlier, it is the direction from which records, memories, and order remain. And that brings us to a remarkable thought. The reason today follows yesterday may not lie in clocks alone, or even in relativity alone. It may lie in the earliest condition of the cosmos. The arrow of time may have been launched by the birth of the universe itself. From that beginning, order has been spreading into disorder, energy has been dispersing, stars have been burning, planets have been forming, life has been appearing, and minds like ours have been trying to understand why time moves in one direction and not the other. In the next episode, we will follow that question even deeper and ask why the early universe was so ordered in the first place. If entropy gives time its arrow, then the low entropy beginning of the universe may be one of the greatest unsolved mysteries in all of physics. Thank you for listening, and thank you for joining me on our journey through time. If you enjoyed this episode, please like and subscribe. It helps the channel and lets me know you'd like more episodes like this. And if the next episode is already on your screen, just click on it now and we'll continue discovering time together. Until then, thanks for listening.